Any questions on anything? You can explain all this stuff to other people. Okay, good.
If lines intersect on the X, you have a.
Wait, what, Brian?
If lines intersect on the X, you have a competitive.
Yeah, so if it intersects here, this is non-competitive. And if it intersects here, this is competitive. Wait, I didn't say that. But anyhow, yeah, this is competitive, intersecting on the y-axis, and intersecting on the x-axis is non-competitive. Yeah, and that's all you need to know. Double inverse graph, and then whatever intersects tells you competitive versus non-competitive. Anything else? Okay. There's actually one more inhibitor. Remember, enzymes are always proteins, but we cannot say that about inhibitors. Inhibitors are often proteins, but they often aren't. So there's no real rule for inhibitors, but enzymes, again, always proteins. So one more type of inhibition. This is called feedback inhibition. And the product of a metabolic pathway inhibits the metabolic pathway. I must confess, I've always wondered why people come in, wait for class to start, and then they walk out. I think they can't do their stuff before class starts. Anyhow, a pathway is something that we have not yet done, but we're going to do it now. It's very rare that that organism has a single chemical reaction. It's very rare. Usually you get a whole sequence of pathways, a whole sequence of reactions. So in this case, reaction A will produce some product B, but B will undergo reaction and produce C, C produce D, D produce P. That's a pathway, a sequence of reactions. Now they can get more complicated easily. For example, B not only might produce C, it can produce F, G, H. It can go off in some other direction. And most of the time, that's exactly what happens. So, at any rate, that's a pathway. Again, very rare to only get one chemical reaction. It's usually a sequence. Now, what this is about here is regulation. We don't always need, and by we I mean any organism, we don't always need to produce every single product all the time. Sometimes we need something, sometimes we don't. Sometimes we need a lot of it, and sometimes not so much. So the idea of it is, for example, at night. Obviously at night we're sleeping, our metabolic level goes down. We don't need to produce as much ATP, for example, at night as we do in the daytime. At night, things slow down. So essentially what's going to happen, I was saying ATP, but it could be any product. We make all this stuff here. E will be our end product, our final product. And we use it, but then at night, when we're sleeping and all that, we will still be using it. You know, we're not dead, we're still doing stuff, but we're not doing as much of it. Things slow down. So what's going to happen then is the E molecule will start to build up in excess. We're making more than we need. Now again, in the daytime, that's fine, we use it. But at night, we're using it, but not as much. Again, things slow down. So we're going to get more of it than we need. It builds up in excess. And what that means is that at a certain threshold level, and that varies, so I can't give you a number, but at a certain threshold level, the excess E molecule becomes an inhibitor. It's not supposed to, that's not its normal function. But when you're getting too much of it, it becomes an inhibitor. In becoming an inhibitor, it's going to feed back to one of the earlier reactions and will inhibit it. Probably stop it. Now I have here a line drawn from E back to the B reaction. I had to draw it to somewhere, but in reality, any one of these reactions could be the ones that are stopped. There's definitely no rule on that either. So So the inhibitor, that's, well, now what is that inhibitor, could feed back at any one of these and stop the reaction. Now, if in fact it's stopping the B reaction here, remember I said B could be leading to F, G, and H. So that sequence might keep going. So this one basically comes to a stop. It's essential, well, it's feedback inhibition, essentially it's negative feedback, which you've had from other classes. Negative feedback, if we're producing too much of something, you stop making it. If you're producing too little, you start making it. It's classic feedback, or negative feedback, is what almost all organisms do, including us. So this is negative feedback. We're making too much E molecule because we're sleeping, or for any other reason. Sleeping is just an example. So it becomes an inhibitor, feeds back here. Again, it could be anywhere. Stops the B reaction. So if you're not producing C, obviously you're not producing D, you're not producing E, and so on.
And then B can jump to F.
No.
No?
Oh, F, yes, yeah, coming down here.
Yeah, it can go.
Yeah, so it's not really jumping, it's just
Okay.
continuing. When I heard you say jumping, I thought you meant it to jump over here. But
Oh,
no, so the other pathway would just keep going, because that's not being inhibited. So that would be all right, but this one's being inhibited. Okay, so in the morning you wake up, and your metabolic level picks up again. You know, you're awake now. So you start using up the excess E molecule. So the E is being stored, it hasn't gone away. The E is being stored, you now need it. You're not making any more yet. It's still inhibited. It's still inhibited. But you've still got the excess. So in the morning when you wake up, you start using the excess, and sooner or later it's gone. You've used it all up. But you still need it. You're still not making any. So what the body does then is it goes and takes any E molecule it can find. Well, the only E molecules left are the inhibitors. So they take the inhibitor molecules, or we do. We take the inhibitor molecules. Those are E molecules. In taking the inhibitor molecule, that removes the inhibition. So the pathway starts up again. Again, it's classic negative feedback. But this is how it's done. So once you remove the inhibitor, the pathway starts up again. You start producing E molecule. That holds you for the rest of the day or whatever until you go to sleep again, and the whole thing starts all over again. But that's feedback inhibition. The product of the pathway inhibits the pathway. But that's really under certain conditions, and that means excess. E can inhibit reaction B in any reaction, but I chose B. Under some conditions, the conditions being excess. You have too much of it. When you have too much of it, it becomes an inhibitor.
So, you know when you talk about anabolism and catabolism, breaking the building
Catabolism.
with my saying wrong?
Saying cannibalism.
Oh, sorry, okay. We're breaking it and rebuilding, right? So when you say there's too much of it, it's inhibiting, so would that be catabolism?
It helps to, well, it could be either one. It could be
Either
either.
one in this.
Yeah.
Both of those
See, this is
described.
simply regulation.
Okay.
So for any process, whether anabolism or catabolism, for any process, you always might be doing too much or not enough. That's just life. So this is a method to regulate. Regulation is a big deal. Otherwise known as information technology, but this is biological information technology. Oh, I thought you had something else. Okay. So again, feedback inhibition. So that's the third of our inhibitors: competitive, non-competitive, and feedback inhibition. Everybody okay before we go to the tough stuff? Everybody's okay. Okay. Not meaning to scare you, but I was saying the truth. The tough stuff is right here, respiration. Now, you've all had it, but I suspect I'll be giving you more detail. It's the complete oxidation of glucose to form carbon dioxide. You all know we breathe in oxygen, we breathe out carbon dioxide. Everybody knows that. Well, that's what this is. And again, I'm pretty sure you've had most of this. Glycolysis, Krebs cycle. I'm not sure about this. You may not have had oxidative phosphorylation. But glycolysis and Krebs cycle, I'm pretty sure you've had. Again, pretty much not in this detail you're going to get. Now, we have kind of an understanding here that when I give you this stuff, you cannot throw things at me. I know you do, but you can't. No throwing things.
From there.
Yep.
But you, just in time.